Okay, starting for this lecture, one other thing that you can do with the ideal gas law is find the molar mass of a gas. There are a couple different ways of finding the molar mass of a gas, because when you think about it, a molar mass of a gas is just the mass of a sample of gas divided by the number of moles of gas in that sample. And any way that you can find those two numbers, you can then take those two numbers and divide them by each other, and you have the molar mass. So one way you can do it is the example we just did, where you rearrange the density equation to solve for molar mass. Its molar mass is dRT over P. So if you have the density of the gas, you can do this. If you don't have the density of the gas, then what you can do is just find the mass of the gas and find the number of moles of gas in the sample separately, and then molar mass is just mass divided by the number of moles. And an example of that follows. Start a new page here. So we've got a sample of gas that has a mass of 827 milligrams and a volume of 0.270 liters at temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Well, and we want to find the molar mass. Okay, so here's our mass right here. And then all we need for the molar mass is to find the number of moles. And this other information here, that's enough for us to find the number of moles. So the mass is 827 milligrams. And you divide by 1,000, and that's 0.827 grams. Okay, so that we've got. For the other quantities, we're going to need to use the ideal gas law. We know that PV is equal to nRT, and if you solve for N, that's going to be PV over RT. And so we need PV and T all in the correct units. That's the big thing here. So P, the pressure was 975 millimeters of mercury. We need that in atmospheres. So you divide by 760. And we end up with 1.28 atmospheres. Let's see what else we need. Temperature, that was 88 degrees Celsius, which we need in Kelvin. So you add 273 and we get 361 Kelvin. And then there was the volume, which we need in liters, which happened to be what they gave us. So we don't have to change that. So N will be P, number of moles will be 1.28 atmospheres times 0.270 liters over 0.08257 liter atmospheres over moles kelvins, and T would be 361 K. So N ends up being 0.01167 moles. And that's the same sample that has a mass of 0.827 grams. And so the molar mass is 0.827 grams divided by 0.01167 moles. And that gives us 70.9 grams per mole as the molar mass. So if you can find the mass and the number of moles, even if it's separate, as long as they're for the same sample of gas, then you can just take mass over number of moles and you've got the molar mass. All right. The next section is about mixtures of gases and how the gases in a mixture behave. Turns out that, of course, because gases all behave the same with respect to temperature and pressure and volume, that when you have a mixture of more than one gas, you can really just add up the total number of moles of all of the different gases you've got, and you can calculate the pressure or the volume based on that. It doesn't matter how many different kinds of gas you've got in there or what gases they are, because they all behave the same physically. And that's because each gas in a mixture acts independently of the others. And that means that each gas in a mixture contributes to the total overall pressure proportional to its numbers of molecules within the mixture. So if 10% of the molecules in a mixture are made up of nitrogen, then nitrogen makes up 10% of the overall pressure. So we'll say if gas X makes up 10% of the molecules in a mixture, then 10% of the overall pressure is due to gas X. And that 10% would be what's known as the partial pressure. Of gas X, or you can just call that P with a little X after it. So P of gas X is number of moles of X times RT over V. If you have a mixture with more than one gas, then say the pressure of the next gas, the partial pressure of gas Y would be equal to the number of moles of Y times RT over V. And the partial pressure of gas Z would be equal to the number of moles of gas Z times RT over V. And the pressure, the total pressure, would be just the total of all of the partial pressures. So Px plus Py plus Pz plus any other partial pressures of any other gases that are present. And collectively, these expressions are known as Dalton's law of partial pressures. Each gas in a mixture exerts a pressure that's proportional to its percentage of molecules in the mixture, and the total pressure of a mixture would be equal to the total of all of the individual partial pressures of all of the gases in the mixture. Okay, the pressure of gas Y, or any of the other gases in the mixture, would be equal to the number of moles of gas Y divided by the total moles of gas in the mixture times the total pressure. Another way of writing this is the pressure due to gas Y is equal to the Greek letter chi, with a little symbol of Y after it, times the total pressure. And chi, which looks kind of like a fancy X, is just the symbol for what's known as mole fraction. Mole fraction would just be the number of moles of the gas you're interested in at the moment divided by the total number of moles of gas. So Ny over N total, in this case, would be the mole fraction of gas Y times the total pressure. So if gas Y makes up 10% of the molecules in the mixture, that means that Ny over N total would be 0.1, and the pressure due to gas Y would be 0.1 times the total pressure, or in other words, 10% of the total pressure. Because 0.1 is, 10%. All right. So what we usually do is take this around and say pressure due to gas Y is equal to the mole fraction of Y times the total pressure. And that is one of the more commonly used expression for Dalton's law. And an example of that would be, for instance, if argon makes up 0.9% of the molecules in air, in other words, chi of argon, or the mole fraction of argon, would be 0.9% divided by 100, which is 0.009. What would the pressure of argon be? When the atmospheric pressure is, say, 745 millimeters of mercury, or 745 torr. Well, pressure of argon is just going to be chi of argon times total pressure. For air, the atmospheric pressure is the total pressure. So what we've got here is 0.009 times 745 millimeters of mercury, and that's 0.009 times 745, which gives us 6.705 millimeters of mercury. And that would be due to just the argon in the air. And you could find the partial pressures for all the other gases that make up the air. And when you add them all together, you would get the total pressure, which in this case would be 745 millimeters of mercury. Okay. We could try another example here. So let's say a sample of hydrogen gas is mixed with water vapor, which is H2O gas, and the total pressure equals 755 torr, and the vapor pressure of water which is another word for the partial pressure of water, at that temperature is 24 torr. The vapor pressure of water actually changes at various temperatures, and you can actually look it up in tables based on what the temperature is. So we'll say at this temperature, whatever the temperature happens to be, the vapor pressure of water is 24 torr. So we're wondering what amount in terms of number of moles of hydrogen gas would be in 1.55 liters of this mixture. At 298 kelvins. So the first thing you want to do is find the pressure of hydrogen alone and use that in the ideal gas law. Because the total pressure is the pressure of the hydrogen and the water vapor. So essentially you have to subtract out the water vapor. Okay, so the pressure of just the hydrogen is going to be the total pressure minus the vapor pressure of the water, which is 755, torr. That is the same thing as millimeters of mercury, but they're calling it torr. Minus 24 torr. And that is, where is it? 731. That's the pressure just from the hydrogen. But we need it in atmospheres. So you divide it by 760 and you get 0.962 atmospheres. So the number of moles of hydrogen will be equal to the partial pressure of the hydrogen times the volume of the entire container over RT. So the partial pressure of the hydrogen is 0.962 atmospheres. That's how we normally deal with mixtures, is by using the partial pressure of one of the components in the mixture instead of trying to divide up the volume between the different gases. Because once you've taken account of the partial pressure of each of the gases in the mixture, you can count the volumes of each of the gases in the mixture as being the entire volume of the entire container. And because of the way gases spread out and intermingle with each other, that's really true, actually, that each gas occupies the entire volume of the container. So you just use partial pressures to account for each individual component in the mixture. So it's 1.55 liters, 0.082057 liter atmospheres over moles Kelvin, times temperature, which is 298, and that's 0.0610 moles of hydrogen. 0.0610. So there's your moles of hydrogen. What we're doing here is very similar to the idea of collecting gases over water. There's a diagram on page 201 that you can check out for how this is done. Since we're not actually going to do it, I'm not going to spend a lot of time on how exactly it's accomplished. But essentially, you'll have a reaction going on in a test tube or a covered beaker or something like that, where a gas is being generated. And you need a way to trap that gas in a way that you can measure it later on. What you usually do is, say, take an empty test tube or something like that and fill it with water, and then you invert it upside down in a beaker of water and take a tube running from the container where the reaction is occurring and stick the other end of that tube up into your test tube. And when the gas is generated inside the test tube where the reaction is occurring, the gas will travel through the tube and up into the inverted test tube, and every bubble of gas that's generated and goes into the test tube that you're using for collecting the gas will essentially push some water out the bottom of the test tube. And you'll notice that the test tube that you're using for collecting the gas will start filling up with gas. And that way you've got your gas trapped, you can measure its volume, and you can find out how much gas you generated. This is known as collecting gas over water, and there is one little complicating factor in doing this, and that is that anytime you have a liquid, you also have a certain amount of the vapor of that liquid, which is a gas, and which will contribute to the total volume and the total pressure of any gas that you're collecting over that liquid. For a liquid like water, the amount of water vapor above water liquid will actually be fairly substantial. So if you want accurate results for the gas that you generated in your reaction, you have to find out how much water vapor is present and subtract it out so that you can find out how much water or how much vapor gas, that is, you produced from the chemical reaction. So collecting gas over water is a convenient way to collect gas produced by a chemical reaction. But as I said, the gas collected is going to be a mixture. It's going to be a mixture of the product gas from your chemical reaction and water vapor. Okay, so to find the number of moles of gas you produced, you have to factor out the water vapor. The easiest way to do that is with Dalton's law of partial pressures. And basically you find the pressure of the product gas and alone, and use that to find the number of moles of product gas from the ideal gas law. Okay, so what we're doing here, first of all, we have to assume that the total pressure inside the collection vessel equals the total pressure outside. And the total pressure outside is just the barometric pressure. You can look at a barometer for that. And the P total inside, which will be the same as the P total outside, is actually the partial pressure of the product gas plus the vapor pressure of water. Okay, as I said, vapor pressures of water are tabulated, and you can look them up in tables based on the temperature. And that's really all you have to know is just the temperature. And so the pressure of the product gas is going to be the total pressure minus the vapor pressure of water. And P total is the atmospheric or the barometric pressure. Okay, and then the number of moles of product gas will just be the partial pressure of the product gas times V over RT. And let's see, we're at about 30 minutes now, so I'm going to stop here, but we'll do an example of that right after we come back.